Alright, ladies and gentlemen, so our last little part here of 6.4 goes into a concept of Newton's law of cooling. Okay? And so we're going to look into it first and foremost. Let's kind of get a little background scenario here. So take into account there's soup. It's left in a cup and it cools to the temperature of the surrounding air. A hot silver ingot immersed in water cools to the temperature of the surrounding water. In situations like these, the rate at which an object's temperature is changing at any given time is roughly proportional to the difference between its temperature and the temperature of the surrounding medium, right? So in the first example, soup was left on the counter, right? And it's going to cool to a temperature at some point in time that is equal to the surrounding air, okay? You sit there and take a silver piece of material, right? A hot silver metal that we're dealing with. And you drop that piece of metal, a silver metal, into water. It at some point will cool to exactly the temperature of that surrounding water. So it is true, all right, that in any of these situations, the rate at which an object's temperature is changing at any given time is roughly proportional to the difference between its temperature currently and the temperature of the surrounding medium. And this concept is known as Newton's law of cooling, okay? And Newton's law of cooling does apply to warming as well, and there actually is an equation for it in addition to it. However, we're going to focus a little bit more so on the cooling side of things. And here is what you see, all right, of the solution to Newton's law of cooling. So let's take into account first and foremost, capital T, all right? Capital T here, to start some things on off with, is the temperature of the object at time t. Temp at time t. Well, that leads us into our next one. Lowercase t focuses on time. And then we look into the other different bits and pieces of it here. And now we look into the T sub s. Well, T sub s focuses on the temp of surrounding medium. The water in the case where we drop the silver on it, or the air in the case of your soup just sitting on the counter, right? There's your T sub s in there. And then the last one we're going to look into is, the last thing that you see is T naught, or T sub 0, and that's going to be your initial temperature, or the temp when T equals 0, okay? And of course, K is our constant of decay or growth in this example. So here's Newton's law of cooling. How can we utilize it in application? Well, a hard-boiled egg at 98 degrees Celsius is put in a pan under 18 degrees Celsius of water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees? Hard-boiled egg, currently at 98 degrees, put in a pan under running water, 18 degrees Celsius, and its goal is to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees? Well, let's take a look into account. Using Newton's law of cooling, first and foremost, the initial of the surface, right? The surface or the medium. What represents the medium in this case? Well, the medium in this case is the water cooling the egg. So T sub s will be 18 degrees. Well, what's the original? Well, when T is 0, aka before you drop it into the water or put the running water over it, you have a 98 degree temperature hard-boiled egg. And so, taking into account the information that we have, now if we want to find how much longer will it take the egg to reach 20 degrees, well, we're going to at some point have to find that value for lowercase t of time. All right, so let's dive on in. We go, and now we're looking at a basic formula of the total temp minus 18 of our surrounding is equal to the original minus the surrounding to the, or times e to the negative k times t. Problem right now, guys, is that we just simply have way too many missing variables. So let's take into account some other information. It says after 5 minutes, the egg's temperature is found to be 38 degrees. So we can use that information, right? After 5 minutes, it's dropped down to 38 degrees. So what do you think that allows us to solve for? Hopefully you're getting to understand that it's going to help us solve for k. Because now we have a value for lowercase t, time, and we have an ending temperature at 38, and that'll help us find out k. And so we can go ahead and use the concept of 38 is equal to 18 plus 80 times e to the negative 5k. All right, and so this will help us actually find the specific values here, okay? And so I want to go ahead and make a quick little, just a quick little change, I guess. Now that we want to find this value for t, I'm going to go ahead and add our 18 on over, and this will simplify, sorry guys, this will simplify on down to 98 minus 18. This is going to give me 80 times e to the negative kt. Well, now I have values for t and for the temperature, so 38 equals 18 plus 80 times e to the negative k times t, which is 5 in this circumstance. So we want to go ahead and find the values in this particular example. So going ahead and subtracting on over, we get 20 equals 80 times e to the negative k 5. Dividing by 80, we get 1/4 equals e to the negative 5k. Just making it a little cleaner for you right there. And then we want to go ahead and get k by itself. So we're going to have to natural log both sides. And we'll see that the natural log of 1/4 equals negative 5 times k. And we want to go ahead and solve for k. And so this will divide by negative 5. And in the end, we'll end up seeing that the natural log of 1/4 equals 1/5 times the natural log of 4. Okay? The only reason why I have natural log of 4 there, guys, is because remember, by definition, in this example, if we have a natural log of 1/4, the natural log of 1/a is equal to the negative natural log of a. So that's where I got my my positive 4, because it was a negative 5, and now I want it in 4. Just because it makes it a little bit cleaner for us, not to deal with a bunch of fractions and things like that. But honestly, it's not 100% necessary either. Alright, so we're not quite done. That was just k. But now we need to find the actual the concept as to how much longer is it going to actually take to get there. And so the egg's temperature at a time t can really be represented at t equals, we've done so far, our 18 plus 80 times e to the k. Well, k in this case now would be negative, all right, 1/5 natural log of 4 times t. So I can use this to find our value for t for any of our particular ones that we're dealing with. And so we want to know what happens basically when t equals 20. So what happens when t equals 20? Well, we have 18 plus 80 times e to the negative 1/5 natural log of 4 times t. 2 equals 80 times the same. Dividing through by 80, we get 1/40 equals e to the negative 1/5 natural log 4 times t. Natural log both sides. We end up seeing here that let me try to separate this out for us. I'm getting a little caught up. So then we have natural log of 1/40 equals negative 1/5 times the natural log of 4 times t. So I'm going to go ahead and multiply by a negative 5 on both sides to get that down. So we have negative 5 times the natural log of 1/40 equals the natural log of 4 times t. Dividing through by the natural log of 4. In the end, we see t will equal negative 5 times the natural log negative 5 times the natural log of 1 over 40, and then divided by the natural log of 4, and we roughly get about 13.3. So it'll take about 13.3 minutes to get that down to 20 degrees. So a real interesting problem as how to use Newton's law of cooling in our concepts of exponential growth and decay. And we're off to the next one.